Planes. In networking, a plane typically refers to a logical or functional layer within a network architecture. These planes help to organize and manage different aspects of network operations. Three common planes in networking include the data plane, control plane, and management plane. The data plane is also known as the forwarding plane or the user plane. This plane is responsible for forwarding data packets from one network device to another. It deals with the actual transmission and switching of data packets, ensuring they reach their intended destinations efficiently. The control plane is responsible for managing and controlling the overall behavior of network devices. It involves tasks such as routing, signaling, and network management. The process of creating a routing table is considered part of the control plane. Essentially, the control plane sets up the paths that the data packets will take through the network. The management plane deals with the configuration, monitoring, and troubleshooting of network devices. It enables network administrators to remotely manage and maintain the network infrastructure, including tasks like device configuration, performance monitoring, and software updates. These planes are often implemented as separate components within networking devices such as routers, switches, and firewalls, each serving a distinct purpose in ensuring the proper functioning and management of the network. Kubernetes overview. Kubernetes is an open-source container orchestration platform designed to automate the deployment, scaling, and management of containerized applications. Originally developed by Google, Kubernetes has become one of the most popular tools for managing containerized workloads in production and computing lab environments. Kubernetes provides a platform of container orchestration for automating the deployment, scaling, and management of containerized applications. It abstracts away the underlying infrastructure, allowing developers to focus on building and deploying applications without worrying about the details of the infrastructure. Kubernetes operates using a cluster architecture consisting of a master node and multiple worker nodes. The master node is responsible for managing the cluster and its components, while the worker nodes host the containers running the application workloads. Kubernetes is built around the concept of containers, which are lightweight, portable, and isolated runtime environments for running applications. It supports popular container runtimes like Docker and Containerd, to which the smallest deployable unit in Kubernetes is a pod, which encapsulates one or more containers. Pods are scheduled onto worker nodes, and containers within the same pod share the same network namespace, IP address, and storage volumes. Kubernetes enables easy replication and scaling of applications by allowing users to define desired replica counts for their deployments. It automatically manages the creation and scaling of replicas based on demand. Kubernetes provides built-in mechanisms for service discovery and load balancing, allowing applications to easily communicate with each other and distribute incoming traffic across multiple instances of a service. Kubernetes also allows users intricate control over resource management and specify resource requests and limits for containers, ensuring fair allocation of CPU and memory resources across applications running in the cluster. Kubernetes continuously monitors the health of applications running in the cluster and is self-healing. If a container or pod fails, Kubernetes automatically restarts it or replaces it with a healthy instance to ensure high availability. However, this should not be confused for a comprehensive self-healing system. For a more advanced approach to this feature, the developer should look into proper self-healing mechanisms to be implemented. Overall, Kubernetes simplifies the process of deploying and managing containerized applications at scale, making it easier for organizations to build and operate modern, cloud-native applications, making it an ideal choice for modern development. Containers in relation to Kubernetes are lightweight, portable, and self-sufficient runtime environments that encapsulate an application along with its dependencies and configurations. They provide a consistent environment for running applications across different computing environments, from development laptops to production servers. Containers are managed by a container runtime such as Docker or Containerd. The container runtime is responsible for creating, running, and managing containers on a host system. Like mentioned in the earlier section, the smallest deployable unit in Kubernetes is called a pod. A pod is a group of one or more containers that share the same network namespace, IP address, and storage volumes. Typically, containers within the same pod are tightly coupled and work together to perform a specific task. Kubernetes orchestrates containerized workloads, meaning it manages the lifecycle of containers running in pods across the cluster. Instead of deploying individual containers, you define and deploy higher-level abstractions like deployments, which manage sets of identical pods, and stateful sets, which manage stateful applications. Deployments are a key concept in Kubernetes for managing the deployment of containerized applications. A deployment defines the desired state of a set of pods, including the number of replicas and the container image to use. Kubernetes ensures that the actual state matches the desired state by creating, scaling, or deleting pods as needed. Kubernetes provides mechanisms for scaling containerized applications horizontally and vertically. Horizontal scaling involves increasing or decreasing the number of pod replicas to match demand, while vertical scaling involves adjusting the CPU and memory resources allocated to individual pods. Kubernetes provides built-in service discovery and load balancing for containerized applications. Each pod is assigned a unique IP address, and Kubernetes manages a set of virtual IPs for services that distribute incoming traffic across pods. This allows applications to communicate with each other and ensures high availability and fault tolerance. Containerization in Kubernetes allows you to specify resource requests and limits for containers, ensuring fair allocation of CPU and memory resources across the cluster. This helps optimize resource utilization and prevents individual pods from hogging resources and affecting the performance of other pods. In summary, Kubernetes provides a powerful platform for managing and orchestrating containerized workloads, allowing you to deploy, scale, and manage applications seamlessly across a distributed cluster of compute resources. Containers are the building blocks of these applications, and Kubernetes abstracts away the complexities of managing containers at scale, making it easier to develop and operate modern cloud-native applications. Networking in relation to Kubernetes. Networking is a crucial aspect of Kubernetes as it enables communication between the various components of a Kubernetes cluster, as well as between applications running within the cluster and external services. Pod networking. Pods within a Kubernetes cluster need to communicate with each other. Kubernetes assigns each pod a unique IP address, and pods can communicate directly with each other using these IP addresses. This is crucial for enabling microservices architectures where different parts of an application run in separate pods. Each pod has its own network namespace, providing isolation and ensuring that containers within the same pod can communicate with each other using localhost. In most Kubernetes clusters, pods can run on different worker nodes, so there needs to be a way for them to communicate across nodes. Overlay networking solutions such as Flannel, Calico, or Weave provide network overlays that allow pods to communicate with each other regardless of the underlying network topology. Service networking. Kubernetes services provide a stable endpoint for accessing a set of pods. Services abstract away the underlying pod IP addresses and provide a single DNS name or IP address that clients can use to access the service. Kubernetes services also offer built-in load balancing, distributing incoming traffic across the pods that back the service. This ensures that traffic is evenly distributed and provides fault tolerance by automatically rerouting traffic away from unhealthy pods. Cluster IP, node port, and load balancer services. Kubernetes supports different types of services, including cluster IP, internal service accessible only within the cluster, node port, service accessible on each node's IP address, and load balancer, service accessible externally via a cloud provider's load balancer. Ingress. Ingress is a Kubernetes resource that manages external access to services within the cluster. It allows for HTTP and HTTPS routing based on host names and paths. Ingress controllers, such as Nginx Ingress Controller or Trafic, handle incoming requests and route them to the appropriate services based on the defined rules. Ingress controllers can also handle TLS termination, decrypting incoming HTTPS traffic and forwarding it to services over plain HTTP. Network policies. Kubernetes network policies allow you to define rules for controlling traffic to and from pods by means of security and access control. Network policies can restrict traffic based on various criteria such as source destination IP addresses, ports, or labels. This provides a powerful mechanism for implementing security and access control within the cluster. External connectivity. Kubernetes applications often need to communicate with external services or users. Kubernetes provides mechanisms for exposing services externally, such as using load balancer services to expose services on cloud provider managed load balancers or using node port services for direct access to services via the node's IP address. Overall, networking in Kubernetes is essential for enabling communication between pods, services, and external resources, as well as for providing security, load balancing, and external access to applications running within the cluster. The flexibility and richness of Kubernetes networking allow for building complex distributed applications while abstracting away many of the underlying networking complexities. MicroK8s. MicroK8s is a lightweight Kubernetes distribution developed by Canonical, the company behind Ubuntu Linux. It is designed to provide a simple and easy-to-install Kubernetes environment for development, testing, and experimentation purposes. MicroK8s aims to offer a fully conformant Kubernetes distribution with minimal overhead and fast setup times. MicroK8s runs as a single-node Kubernetes cluster by default, meaning it installs all necessary Kubernetes components on a single machine. This makes it ideal for local development and testing scenarios where you don't need a full multi-node cluster. MicroK8s can be installed with a single command, x sudo snap install MicroK8s, making it easy to set up a Kubernetes environment on your local machine or a virtual machine. It uses lightweight Linux containers, LXC, to isolate Kubernetes components, resulting in fast installation times. MicroK8s aims to provide a fully conformant Kubernetes distribution, meaning it supports the Kubernetes API and functionality as defined by the Kubernetes upstream project. This ensures compatibility with standard Kubernetes tools and workflows. MicroK8s comes with a range of optional add-ons and extensions that can be enabled to extend its functionality. These include features such as DNS, storage, monitoring, dashboard, registry, and more. Users can enable or disable these add-ons based on their requirements. MicroK8s is distributed as a snap package, a containerized software package format that includes all dependencies and ensures consistent behavior across different Linux distributions. This makes it easy to install, upgrade, and manage MicroK8s using standard Linux package management tools. MicroK8s can be installed on various Linux distributions, including Ubuntu, Fedora, Debian, CentOS, and others. Its lightweight nature and single-node architecture make it a portable solution for running on laptops, desktops, virtual machines, and cloud instances. MicroK8s is well suited for development and testing scenarios, allowing developers to quickly spin up Kubernetes clusters for building, testing, and debugging containerized applications. Its simplicity makes it accessible to developers who may not have extensive Kubernetes expertise. MicroK8s is designed with security in mind and comes with default configurations that adhere to best practices for securing Kubernetes clusters. It provides features like RBAC, role-based access control, and network policies out of the box. Overall, MicroK8s provides a convenient and lightweight way to run Kubernetes locally or in small-scale environments, enabling developers to quickly get started with Kubernetes development and experimentation. MicroK8s Networking. Networking in MicroK8s is quite similar to networking in a standard Kubernetes environment, as MicroK8s aims to provide a fully conformant Kubernetes distribution with minimal overhead. However, there might be some differences in the way networking is configured and managed due to MicroK8's focus on simplicity and ease of use. MicroK8s typically uses a default networking setup based on the Flannel CNI Container Networking Interface plugin, which is a common choice for overlay networking in Kubernetes clusters. Similarly, many Kubernetes distributions use Flannel or similar overlay networks as the default networking solution. MicroK8s assigns each pod a unique IP address from the Flannel network range, just like in standard Kubernetes. Pods can communicate with each other using these IP addresses, and network isolation between pods is maintained. The network namespace of each pod is also isolated, ensuring that containers within the same pod can communicate using localhost but are isolated from containers in other pods. Kubernetes services in MicroK8s are assigned cluster IP addresses, and service networking is managed in a similar way to standard Kubernetes. Services provide a stable endpoint for accessing a set of pods, and service discovery and load balancing are handled by Kubernetes. Ingress resources can be used to expose services externally, and ingress controllers such as Nginx Ingress Controller can be deployed to manage external access to services. MicroK8s supports exposing services externally using node port or load balancer services similar to standard Kubernetes. Node port services expose a service on each node's IP address at a specific port, allowing external access to services. Load balancer services create external load balancers if supported by the environment to expose services externally. MicroK8s supports Kubernetes network policies, which allow you to define rules for controlling traffic to and from pods. Network policies work in the same way as in standard Kubernetes, providing security and access control within the cluster. While the overall concepts and functionalities of networking in MicroK8s are similar to standard Kubernetes, the specific configuration and management might differ slightly due to MicroK8s' focus on simplicity and its default choices for networking solutions. However, the fundamental principles remain consistent, making it easy to transition between MicroK8s and other Kubernetes environments. MicroK8s Services. MicroK8s provides a variety of services, but there are several essential ones that are commonly used and are crucial for basic Kubernetes functionality. These services form the core of MicroK8s and enable you to deploy, manage, and operate containerized applications within a Kubernetes cluster. The Kubernetes API server, KubeAPI server, is the central management component of a Kubernetes cluster. It exposes the Kubernetes API, which allows users to interact with the cluster to create, update, and delete Kubernetes resources such as pods, services, deployments, and more. Kubernetes is the primary node agent that runs on each node in the Kubernetes cluster. It is responsible for managing the containers and pods on that node. Kubernetes communicates with the Kubernetes API server to receive instructions on which containers to run and manage. MicroK8s supports multiple container runtimes, including Containerd, Docker, and CRIO. These container runtimes are responsible for pulling container images, creating containers, managing container lifecycles, and executing containerized applications. DNS, Domain Name System, is essential for service discovery within the Kubernetes cluster. MicroK8s provides either Kubernetes DNS, KubeDNS, or KoraDNS as the DNS service, allowing pods to communicate with each other using DNS names. The Kubernetes dashboard is a web-based user interface that provides visibility and management capabilities for the Kubernetes cluster. It allows users to view cluster resources, create and manage deployments, services, and pods, and monitor cluster health and performance. MicroK8s includes basic support for storage using local storage, host path volumes, or external storage providers. This enables the creation of persistent volumes that can be mounted by pods to store data. MicroK8s uses the Flannel CNI Container Networking Interface plugin for networking, providing overlay networking for communication between pods. This allows pods to communicate with each other across nodes in the cluster. An ingress controller manages external access to services within the Kubernetes cluster. MicroK8s includes an ingress controller that allows you to expose HTTP and HTTPS services to external clients and route incoming requests to the appropriate services based on defined rules. These essential services form the foundation of MicroK8s and enable you to deploy, manage, and operate containerized applications within a Kubernetes cluster. Depending on your specific requirements, you may also enable additional services and features provided by MicroK8s to extend its functionality.